Here is a short video on Chapter 14 on heat and calculation of heat. Section 14-1 is on heat as energy transfer. Heat is energy transfer from one object to another because of a temperature difference of the two objects. Heat always goes from the hot object to the cold object. So whenever you're cold, you should snuggle up to somebody next to you that's warmer so that you can get some of their heat transferred to you to warm your temperature up. The unit of heat in the SI system is the calorie, or the kcal. We're going to try and stick to joules in this chapter. 4.186 joules is the equivalent of 1 calorie. A kcalorie is 1,000 calories. Therefore, in 1 kcalorie, there's 4,186 joules. Make sure you read your problems carefully to find out if you're given kcalories or kilojoules or joules or calories. 1 calorie is the amount of heat necessary to raise the temperature of 1 gram of water by 1 degree Celsius. That's the definition of the calorie. Let's take a look at internal energy. Internal energy is best known as thermal energy. Thermal energy is the total energy of a gas. The internal energy, or the thermal energy, of an ideal gas is given by this equation. U is equal to 3/2 nRT, where N is the number of moles, R is the universal gas constant, and T is temperature. If a gas is molecular rather than atomic, molecules not only vibrate, but they also rotate. We learned that in the previous lecture on Chapter 13 about particle motions as we raise the temperatures up. Section 14-3 is where we start doing our mathematical calculations, and they will be on calculating heat. Specifically, we'll be calculating specific heat. The amount of heat required to change the temperature delta T of a material of mass m is given by this equation. We're going to label this equation number 1 because there's 2 equations of heat that we will be going through. One of them is a heat where we have a temperature change. You're having one body snuggle up to another body, take some of the heat from the other body, bring it into the colder body. The two bodies are at 2 different temperatures. You're trying to come to one equal temperature, or a thermal equilibrium temperature. So the bodies are at the same uniform temperature. So we need a transfer of heat from the hot body to the cold body to warm the cold body up. So we would use this equation number 1 because there is a temperature change involved. M is the mass of the object that's being cooled or heated. C is called the specific heat. And C, you're going to look up in tables. On the left, in table 14-1, lists specific heats C. And notice the units. They're given by kcals per kilogram degree Celsius, or I suggest using the left column, joules per kilogram degree Celsius. I've already blocked off some of the values for specific heat that we will use in this lecture today. We will be looking at an iron pot, where the specific heat is 450 joules per kilogram degree Celsius. We'll be looking at ice, where the specific heat is 2100 joules per kilogram degree Celsius, and we'll be looking at liquid water, where the specific heat is 4186 joules per kilogram degree Celsius. Be sure to keep your units in mind. Table 14-2 lists specific heats of gases. If you'll be looking at gases such as carbon dioxide, helium, oxygen, steam, water vapor, or nitrogen, you need to look up the specific heats of gases, whether you're at constant pressure or at constant volume. Now, how do we determine specific heat? Well, you can read section 14-4 on calorimetry. On the left is a calorimeter. The instrument to the left is a calorimeter, which makes quantitative measurements of heat exchange. A sample is heated to a well-measured high temperature, plunged into the water, and the temperature equilibrium is measured. This is how we find the specific heat of a sample. Once we find the specific heat of a sample, we fill it in this table on the left based on the body that we are using as our substance in our calculation of specific heat. Let's look at a particular example. We want to find out how much heat is generated in units of joules to raise the temperature of an empty 20 kilogram iron vat from 10 degrees Celsius to 90 degrees Celsius. First thing you need to know is we are looking for heat. The question says how much heat. Since we have heat and we have a temperature change, we know we want to use this equation number 1. Q is equal to mc delta T. Now it tells us we have an iron vat. So we have a pot that's made of iron. So we need to go to the table in the textbook and look up the specific heat of iron, which is 450 joules per kilogram degrees Celsius. Now we need to solve. We're given the mass of 20 kilograms, an initial temperature of 10 degrees Celsius, a final temperature of 90 degrees Celsius. We want to find heat, which is given the letter Q. We're using this equation number 1. Q is equal to mc delta T, where delta is still final minus initial, so our delta T is T final minus T initial. We put our mass in of 20 kilograms, our 450 joules per kilogram degrees C for a specific heat that we looked up in the table, and we write our temperature difference down. Notice that our specific heat is given in units of deltas of degrees Celsius. Therefore, we're going to leave our temperature change in degrees Celsius. We multiply everything out, 20 times 450 times 80, and we divide our units out, and we see the only unit that we're left with is joules. So heat has joules as the unit, and our value is 720,000 joules. We want to get out of joules and put it into kilojoules, so our conversion is 1,000 joules per kilojoule, and our value for heat is 720 kilojoules. We need 720 kilojoules of heat to add to the vat that contains 20 kilograms of iron to raise the temperature from 10 degrees to 90 degrees Celsius. Now we have a second equation for heat, and that's called latent heat. And this is whenever you have a phase change. So here we're looking at a diagram of temperature on the left axis, and we have heat added in kcal on the right, on the horizontal axis. Here we have ice in blue, and there is a temperature range where we have ice from 20 to 100 heat being added. And then we have a water range from 100 to 200 kcals where heat is being added. And on the left is our temperature change. So whenever we're at ice, we're looking at 0 to minus 40 degrees Celsius. And whenever we're looking at water, we're looking at minus 40 to 100. So how we read this graph is we add heat to our water ice, and eventually our water ice will convert into water. At a temperature, at heat added of 100 kcals and a temperature of 0 degrees Celsius, we have got a phase change. And this phase change is occurring at this particular heat and at this particular temperature. So we are undergoing a phase change from ice into liquid. So we have what's called latent heat, or heat being added where temperature is not changing, but we're going from a solid to a liquid or a liquid to a gas or vice versa. If you're going to go from a solid to a liquid or a liquid to a solid, we call that latent heat diffusion if we're going from a solid to a liquid. But if you're going from a liquid to a solid or solid to a liquid, you can turn to table 14-3 and look up the value for conversion, and notice that the units are given in kilojoules per kilogram. we'll be looking at water. And so the value for latent heat at kilojoules per kilogram is 333 kilojoules per kilogram. If you're going to look for vaporization, where you're going to go from liquid to vapor, water vapor, or you're going to go water vapor to water liquid, then you would look up the heat of vaporization value for latent heat, which is this value right here. The total heat required for a phase change depends on the total mass and the latent heat. So we have this equation number 2, where Q is equal to mass times latent heat. You need to know the mass that you want to change from one phase to another, whether a solid to a liquid to a gas, or a gas to a liquid, or a liquid back to a solid. And you look up your conversions in the table for your latent heats. Now there's some problem-solving keywords to keep in mind, and you can go through these keywords on your own, but the one that I want to highlight is number 5. Make sure that each term is in the right place and that all the temperature changes are positive. Even though we have delta T as final minus initial, delta T may end up being negative, but you have to make sure all the temperature changes are positive in your equations. Let's take a look at an example. We're going to look at 1.5 kilograms of water at 20 degrees Celsius. So basically you have water that's at room temperature, and you want to take this water from your room and you want to put it in a freezer. How much heat energy is needed to freeze this water? You want to pull the heat out of the water, and you want to lower the temperature of the water to 0 degrees Celsius, where it's going to then go into latent heat. It's going to convert from water into ice. And then you want to continue lowering the temperature down to minus 12 degrees Celsius. So let's take a look at our given. We're given a mass quantity of water of 1.5 kilograms. Our initial temperature is 20 degrees Celsius, and our final temperature is minus 12 degrees Celsius. We're going to drop the temperature of the water down below freezing. We want to find the total amount of heat needed to be removed from that water to make it into ice at minus 12 degrees Celsius. So we have to go through 3 Q equations to account for all of the total amount of heat that's going to be removed from this water. The first Q that we need to go through is MC delta T. That's equation number 1, because we're dropping the water temperature from room temperature, 20 degrees Celsius, down to freezing to 0 degrees Celsius. That's the first delta T. Then we go through a phase change at 0 degrees Celsius. So we're not going to change the temperature. We're just going to remove heat from the body, the water, to convert it from a liquid to a solid. So we need to account for the latent heat. Then the last thing we're going to do is we're going to continue to drop the temperature from 0 degrees Celsius to minus 12 degrees Celsius. So we have another temperature change. So we go back to equation number 1, where Q3 is MC delta T. Our total amount of heat that we need to remove from the water is Q1 plus Q2 plus Q3, which is equal to M parentheses C delta T1 plus L plus C delta T2. So our mass quantity is 1.5 kilograms. We look up in the table for C at water, and water is 4186 joules per kilogram degrees Celsius. We're going to have a temperature drop of 20 degrees Celsius. We add on our latent heat, 333 kilojoules per kilogram. Notice that we have kilojoules when we look up our latent heat, but when we look up our C value, we have joule values. And then once again, we want to lower the temperature down of our ice by 12 degrees Celsius. So we add in our third Q. We look at all our multiplications, we multiply everything out, and we get a value of 660,000 joules, which if we convert to kilojoules, we divide by 1,000, we get the total amount of heat is 660 kilojoules. That's the amount of heat that needs to be removed from the water to convert it from room temperature all the way down into ice at minus 12 degrees Celsius. Now the last part of this text in this chapter 14 is on 3 modes of energy transport. There's only 3 types of modes, and that is conduction, convection, and radiation. Let's look at conduction first. Conduction is when you have heat being transferred through a material. You can't see the heat being transferred, but you can feel the heat being transferred. A good example is getting a cheap metal pot from the Dollar Tree, filling it up with water, putting it on the stove, and turning the stove on to boil the water. After a few minutes, if you start to feel the handle or the pot, you'll feel that the part of the handle or the pot is getting warm, but the edge or tip of the handle is cooler. So the metal in the pot is made of molecules, and those molecules are bouncing around, vibrating into one another, and they are transferring heat down through the handle of the pot by the collisions of these molecules. Now, where the heat source is added, which is the bottom of the pot, that's where you're going to have the highest amount of particles bouncing into one another, transferring energy. Since the handle, the edge of the handle is so far away from the heat source, it's going to have the fewest amount of particles bouncing around. Therefore, it's going to have the coldest temperature. So conduction is from the vibration and bouncing of molecules in the metal, and it gets transferred down through the handle by vibrations and collisions of particles in the metal. Heat conduction can be visualized as molecular collisions. So this is your model. We just think of heat being transferred through a metal pot by the collisions of these particles. In this case, we're going to be looking for heat flow, which heat is given by Q, but we want to know per unit time. So we're looking for a rate of heat transfer. So this is where it's called energy transport. How do you transport energy from part A or point A to point B? This method that we're going to look at is by conduction. So we want to know how long it's going to take to transfer the heat from the body of the pot down the handle to the tip of the handle. We would look at this equation here, which is the amount of heat that's being transferred per unit time. That is equal to Ka times the change in temperature divided by the length. So if I had my pot of water here, my length of the handle would be from where the body connects to the handle to the tip of the handle, and that would be my length L. I'm looking for a temperature change from one end of the pot to the other end, from the tip of the handle to where it connects to the body of the pot. So that's my temperature change along the length of that handle. I'm looking for the area of the handle, and I'm looking for K, where K is our thermal conductivity constant. Once again, you're going to look up the values in our tables. So table 14-4 is on our thermal conductivities. You look up the type of conducting object that we have. In this case, we have a metal pot. So let's say we've got a cheap aluminum pot. Well, there's aluminum. And here's our values. You look it up and make sure you pay attention to your units. It's joules in this case. And we have degrees Celsius in the denominator. Sometimes we have looking at building materials. And building materials have on them stamped R values. Those R values are a function of the length of the material and this thermal conductivity constant K. For example, you could have insulation. If you look at insulation, it will have an R value on it. The R value is determined by this equation, length divided by K, and you're going to look up the R value depending on the material in your problem. Materials with large K are called conductors, and materials with small k are called insulators. And that's your difference between conductors and insulators. is your K value. Let's look at our second mode of energy transport, and that is convection. Convection is the only one where we can actually see heat being transferred. Let's take a look at a pot of water. Here we have a flame, and the flame is heating up the bottom of the pot. Now the pot is made of metal, so you're going to have heat conduction going through the pot by the vibration and bouncing of molecules in the metal. And that heat is going to heat up the bottom of the pot. That's where our hottest water is going to be. The first thing that happens is you're going to form bubbles at the bottom of your pot. And then those bubbles will eventually rise to the top of the pot. The motion of the particles, these gas particles rising to the top of the pot, is going to push water to the bottom of the pot, and that's going to start our rolling boil. Once the bubble reaches the top of the pot, it's going to burst, and it's going to release that steam, and that's where we get our steam from. It's our water vapor gas. And it's a molecular gas because you've got water breaking apart into steam, but it's still going to be a water vapor steam. It's still going to be a molecular steam. So convection occurs when heat flows by the mass or bulk movement of molecules from one place to another. In this case, we're looking at water transferring heat from the bottom of the pot where it's hotter to the top of the pot where the water is cooler. And we're going to move the water around. It's going to go down to the bottom of the pot, pick up heat, go up to the top of the pot, throw it off at the top, and steam. Go back to the bottom of the pot, pick it up heat, go to the top of the pot. You're transferring heat from the bottom of the pot to the top of the pot by the method of convection. Convection may be natural or it may be forced. For example, a fan that blows out air at the register in your house would be forced air. That's forced convection. Natural convection would be where just you have gases rising up off the surface of the land of Earth, for example. Our body temperature is regulated by blood. Blood runs close to the skin surface and transfers heat via convection, evaporation, and radiation, all three. So if you've ever been in a spin class and you're working out and you have a lot of sweat that develops on your skin, the very first thing you want to do is you want to remove the sweat off your skin. Get that water off your skin so your body can cool by radiation and evaporation. If you've got all that water molecules sitting on the surface of your skin, it will be hard for your body to transfer heat because you have that water in the way. You need to remove the water off your body to let your body cool quicker. Then you drink your water to rehydrate. First thing you should do to cool your body off is get rid of all of that water off your body so your body can naturally cool by radiation. So let's look at the third form of energy transport, radiation. You're most familiar with the sun as our example of radiation. If you go stand outside and stick your arms out on a bright sunny day, you can feel the heat coming from the sun. That is an example of energy transport by radiation. You can't see the heat rays coming from the sun through Earth's atmosphere down to your arms, but you can feel it. So radiation you cannot see, conduction you cannot see, but convection you can see because it's bulk mass motions of objects. Radiation you feel the heat from the sun. The sun radiates at a temperature of 5778 Kelvin. If you are sitting in a place that is cold, your body radiates more heat than it can produce, and you will start shivering and your metabolic rate will increase until you put on warmer clothing. Or you snuggle up next to somebody that's warmer and you rob them of their body heat to make you warmer. If you are in the sunlight, which is the picture on the left, the sun's radiation will warm you. In general, though, you will not be perfectly perpendicular to the sun's rays. The sun's rays will be coming in at an angle theta to the ground. So we want to know the amount of heat that's being transferred by the sun per unit time. Well, that is 1,000 watts per meter squared multiplied by the emissivity E, multiplied by the area A, and the angle that the light is coming in at. The area A is your surface area that's being exposed to the sunlight. E is the emissivity, and it's a number between 0 and 1. Black objects have an emissivity of 1 because they absorb most of the sunlight. But if you're wearing white clothes or shiny metal clothes, then you're going to reflect most of that sunlight and your emissivity will be down to 0. So it depends on what you're wearing where that emissivity value comes in. Thermography is the detailed measurement of radiation from the body. It can be used in medical imaging. Warmer areas may be signs of tumors or infection. Cooler areas on the skin may be sign of poor circulation. Here on the left, we're looking at good circulation. We can see circulation going down into the digits of the fingers and on the surface of the hand. But in the right image, we see poor circulation. Notice that the hands are much cooler. We don't see very good circulation in the hands. They probably have a constriction in their wrists that's not allowing the blood flow to pass through, or the veins are more in the interior of the body than on the surface. But they're limiting their amount of heat that's being transferred to their hands, so their hands are always going to be cold to them. Energy radiated from objects like the sun is from electromagnetic waves and is found to be proportional to the fourth power of temperature. Our equation that we use for radiation transport and the heat energy is Q over T is equal to the emissivity multiplied by the Stefan Boltzmann constant multiplied by the area multiplied by the temperature to the fourth power. We're looking at the amount of joules being radiated per second or absorbed per second, and it's going to depend on the body's area and emissivity. What is the color of the body? Is it dark? Is it light? So you need to know your fudge factor from 0 to 1. And this is a constant, the Stefan Boltzmann constant. All you need to know is the surface temperature of the body. Let's take a look at an example. A human of surface area 1.5 meters squared and 34 degrees Celsius is sitting in a dark room, the walls of which have a surface temperature of 15 degrees Celsius. What is the body's heat loss rate via radiation? Assume an emissivity of 0.7. So we're going to use this equation. Q over T is equal to the emissivity times the area times sigma delta T to the fourth. We're given an area of 1.5 meters squared. We're given the human's temperature is much hotter, 34 degrees Celsius. We're given the wall temperature is 15 degrees Celsius. And we're given an emissivity of 0.7. We want to find the rate that the energy is being lost from the human. The human is hotter, the walls are cooler. So we want to transfer the heat from the human to the walls or to the air in the room. So we want to find the heat loss rate by the human. Well, it's just sigma A, it's epsilon A sigma delta T to the fourth. Our emissivity is 0.7. Our surface area of the human is 1.5 meters squared. Sigma is the constant, is 5.67 times 10 to the minus 8th watts per meter squared Kelvin to the fourth. And we notice that our temperature here is in Kelvin to the fourth. Therefore, our delta T must also be in units of Kelvin. So we transfer our degrees Celsius into Kelvin. All we do is take our 34 degrees Celsius, add on 273, and we convert that to 307 Kelvin. Likewise for the wall, we transfer it to 288 Kelvin. Our delta T is only 19 Kelvin, but we have to take the whole thing to the fourth power. So this means we have to take 19, multiply it by 19, multiply it by 19, multiply it by 19 4 times because it's to the fourth power. We multiply everything out and we end up with the amount of heat that's being transferred to the room from the human at a rate of 120 watts. That means 120 joules per second. It's a high rate of heat transfer. This human's going to cool off rather quickly. So this is a chapter that's on heat and heat loss or heat gain, the rate that heat's being lost or the rates that heat's being gained by radiation or by conduction. The one mode that we're not going to have an equation for is convection, because it is too difficult of a problem to cover at this level. So you will either deal with radiation loss or gain, or you will deal with conduction loss or gain. In either case, you're going to be looking up values in a table. You'll have a temperature difference. You need to know the area. And in the case of conduction, you need to know the length. And that ends this chapter.